In 2013, astronomers discovered a strange, faint pink-colored world orbiting a sun-like star 57 light-years from Earth. It was one of the coldest objects of its kind ever directly photographed, and its unusual rosy color immediately earned it a nickname that stuck, the Pink Planet. For more than a decade afterward, that's mostly all anyone knew about it. A color, a rough size, and a mystery nobody could crack. Multiple research teams tried. Astronomers pointed some of the largest, most powerful ground-based telescopes on Earth at this object, dedicating entire nights of precious observing time to it, hoping to capture enough of its faint light to actually analyze what its atmosphere was made of. Every single attempt failed. The planet's own host star was simply too bright, too close, and too overwhelming, drowning out the planet's faint signal every time. In June 2026, a team using the James Webb Space Telescope finally succeeded, and it took them about 2 hours. What they found wasn't just an answer to the color mystery, it was direct evidence of something scientists had only theorized about for more than 15 years, clouds made of actual salt, floating in the atmosphere of a cold world outside our own solar system, the first time anything like it has ever been directly confirmed. By the end of this video, you'll understand exactly what made this object so hard to study for over a decade, how JWST cracked it in a fraction of the time previous attempts required, and why the answer still leaves one genuinely fascinating mystery about this world completely unresolved. This is a genuinely satisfying kind of space story. Not a danger, not an unresolved crisis, but a real, patient scientific puzzle that took over 10 years, multiple failed attempts, and one of the most advanced telescopes ever built to finally crack open. To understand why this discovery took more than 10 years, you first need to understand exactly what made this object so unusually difficult to study in the first place. The Pink Planet, formerly designated GJ504b, was discovered in 2013 orbiting a sun-like star called GJ504, located about 57 light-years from Earth. It was found using a technique called direct imaging. Rather than detecting a planet indirectly through the way it dims its star's light or tugs on its star's position, direct imaging means actually capturing a picture of the planet itself, separate from its star, something that remains extraordinarily difficult and relatively rare in exoplanet science even today. Direct imaging is genuinely one of the hardest ways to find and study a planet, precisely because of the enormous contrast problem involved. A star is typically millions or even billions of times brighter than any planet orbiting it. And from the distance of Earth, that planet usually sits so close to its star in terms of apparent position in the sky that its faint light gets completely lost in the star's overwhelming glare. Astronomers who attempt direct imaging have to rely on specialized instruments and techniques specifically designed to block out or subtract a star's light as precisely as possible, while still preserving enough of the much fainter planetary signal to actually study it. GJ504b's original 2013 discovery was itself a notable achievement for exactly this reason. But capturing a single detection image, turned out, was a very different challenge than gathering enough detailed light to actually determine what its atmosphere was made of. Almost immediately, GJ504b presented scientists with an identity crisis. With a mass estimated at roughly 25 times that of Jupiter, it sits right on the blurry, poorly defined boundary between what counts as a giant planet and what counts as a brown dwarf. A kind of failed star, too small to sustain the nuclear fusion that powers a true star, but often much more massive than even the largest planets. Because of that ambiguity, astronomers have generally referred to it using a deliberately vague, hedge-your-bets term, a planetary mass companion, acknowledging that its exact category remains genuinely uncertain. The specific line astronomers typically use to separate a giant planet from a brown dwarf involves the ability to fuse deuterium, a heavier form of hydrogen, in an object's core, a process that generally requires a mass somewhere around 13 times that of Jupiter to sustain. Below that threshold, an object is usually classified as a planet. Above it, most astronomers would call it a brown dwarf, regardless of how it actually formed. At roughly 25 Jupiter masses, GJ504b sits comfortably above that particular numerical boundary, which is part of why some researchers have leaned toward classifying it as a brown dwarf companion rather than a true planet, even before this new atmospheric data further complicated the picture. But mass alone has never been a fully satisfying way to draw this line, since an object's formation history, whether it coalesced gradually within a disk of material like a planet, or collapsed directly from a cloud of gas like a star, arguably matters just as much as its final mass, if not more. It also turned out to be one of the coldest objects of its kind that astronomers had ever directly photographed. That combination, extremely cold, extremely faint, and sitting incredibly close, from our point of view, to a much brighter host star, made it a uniquely difficult target to study in any further detail. Multiple research teams attempted exactly that over the following decade, using some of the largest and most sophisticated ground-based telescopes on Earth. According to Anish Baburaj, an exoplanet researcher at Northwestern University who would eventually lead the team that finally cracked the case, other astronomers had previously observed the object for an entire night, using some of the biggest telescopes in the world, specifically trying to obtain a usable spectrum of its light, and they simply couldn't see it clearly enough to get one. That's the specific mystery that sat unresolved for more than a decade. Astronomers knew this strange, cold, pink world existed, but had no way to actually determine what its atmosphere was made of, why it appeared the color it did, or even to fully settle the more basic question of whether it should be classified as a planet or something closer to a failed star. It's worth appreciating just how frustrating that gap must have been for the astronomers involved. GJ504b wasn't some barely detected smudge of light that vanished after a single observation. It was a confirmed, repeatedly rephotographed object, sitting there in the data known to exist with confidence, and yet fundamentally unreadable, using every available instrument for well over a decade. That's a genuinely unusual situation in modern astronomy, where most confirmed discoveries get followed up with progressively more detailed observations within just a few years. GJ504b instead sat as a kind of open invitation for over 10 years, waiting specifically for an instrument capable enough to finally answer the basic questions its 2013 discovery had raised but couldn't resolve. In June 2026, Baburaj and a team of collaborators, including Marshall Perrin of the Space Telescope Science Institute, who designed the specific observing program used for this target, and researchers spanning multiple institutions across the JWST science community, published their results in the Astronomical Journal. Using JWST's near-infrared spectrograph, specifically designed to separate incredibly faint light from an object sitting very close to a much brighter star, the team captured a usable spectrum of GJ504b in roughly 2 hours of observing time. To appreciate how significant that is, it helps to directly compare it against everything that came before. Ground-based telescopes, some of the largest and most advanced observatories humanity has ever built, had already tried and failed to capture the same kind of data using entire nights of dedicated observing time, many multiples of the 2 hours JWST needed. That difference reflects a combination of factors. JWST operates above Earth's atmosphere entirely, eliminating the constant blurring and interference that ground-based telescopes have to fight through, no matter how advanced their instruments and adaptive optic systems become, and its instruments were specifically engineered for exactly this kind of high-contrast observation, separating an extremely faint companion object from the overwhelming glare of a much brighter nearby star. This particular observation was part of a broader JWST research initiative, specifically focused on testing and refining high-contrast imaging techniques, sometimes referred to within the research community by the shorthand JWST-TST, reflecting its role as part of ongoing efforts by the JWST telescope scientist team to push the observatory's capabilities in exactly this kind of challenging observation. Marshall Perrin, who designed the specific observing program used to study GJ504b, serves on that same telescope scientist team, which was directly involved in developing JWST's instruments and continues supporting its ongoing science operations. That institutional expertise in pushing the boundaries of high-contrast observation is part of why this particular team was well-positioned to succeed, where previous ground-based attempts had repeatedly fallen short. The spectrum itself, essentially a detailed breakdown of exactly which wavelengths of light the planet's atmosphere absorbs and emits, revealed a genuinely rich chemical picture. The data showed clear evidence of water vapor, methane, carbon dioxide, and ammonia, along with more subtle traces of additional compounds including hydrogen sulfide and different isotopic forms of carbon monoxide. That's a considerably more complex atmospheric chemistry than a simple, featureless spectrum would have suggested, and it gave the research team enough information to start piecing together a genuinely detailed picture of conditions on this distant, faint world. Each of those detected molecules carries its own scientific significance. Water vapor and methane are common building blocks in the atmospheres of cold giant planets throughout the galaxy, including within our own solar system. And their presence here helps confirm that GJ504b's chemistry broadly follows patterns astronomers already understand reasonably well from studying Jupiter and Saturn. The detection of different isotopic forms of carbon monoxide is particularly valuable for a more specialized reason. The specific ratio between different carbon isotopes can sometimes offer subtle clues about where and how an object originally formed, since different formation environments can leave slightly different isotopic signatures behind. Extracting that kind of fine detail from an object this faint and this far away represents a genuinely impressive piece of observational work, one that simply wasn't possible using any instrument available before JWST. The team also used their new data to refine estimates of the system's age, calculating it at somewhere between roughly 2, 5, and 4 billion years old. That's a meaningfully important number, because giant planets and similar objects start out extremely hot, right after they form and gradually cool down over enormous stretches of time, meaning an object's current temperature, combined with a reliable age estimate, lets scientists work backward to calculate its true mass with much greater confidence. This older, more precisely dated age estimate ended up supporting the idea that GJ 504b is genuinely heavier than some earlier estimates had suggested, reinforcing its position right at that ambiguous boundary between giant planet and brown dwarf. Here's where the story gets genuinely unusual, and where more than 15 years of pure theoretical speculation finally met direct, real observational evidence. Once Babaraj's team had their spectrum in hand, they ran it through detailed atmospheric simulations, trying to match the data against various models of what GJ 504b's atmosphere might actually look like. Initially, something didn't add up. Models without any clouds in them simply couldn't reproduce the specific pattern of light the spectrum showed. As Babaraj described it, the mystery only resolved once the team started introducing different types of clouds into their simulations. They tested several different cloud compositions, and one type in particular produced a dramatically better match than any of the others: clouds made of salt. That result matters enormously because it represents the first time astronomers have directly confirmed the presence of salt clouds in the atmosphere of a cold planetary mass object anywhere outside our own solar system. Scientists had actually proposed this exact possibility more than 15 years earlier, theorizing that certain cold, chemically rich atmospheres might be capable of forming clouds out of alkali salts, rather than the more familiar water, ammonia, or methane clouds found throughout our own solar system. For over a decade and a half, that idea remained purely theoretical, a plausible prediction with no direct observational confirmation anywhere. GJ 504b's spectrum finally provided that confirmation. It's worth understanding a little about why salt clouds are considered such an exotic possibility in the first place. In the relatively cold, low-pressure environments found deep within a planet's atmosphere, most familiar substances either remain as gas or freeze directly into solid ice particles, forming clouds made of water ice, ammonia ice, or methane ice, depending on the specific temperature and chemistry involved, the kinds of clouds already well documented throughout our own solar system's planets and moons. Alkali salts, compounds involving elements like sodium and potassium, behave differently under specific temperature and pressure conditions, theoretically capable of condensing into their own distinct type of cloud layer under just the right circumstances. Predicting exactly which cold, distant worlds might have the right conditions to form this specific kind of cloud has remained a largely theoretical exercise for astronomers, given how difficult it's been to gather detailed enough atmospheric data on cold, faint objects to actually test the idea directly. As Babaraj put it, this is the first time researchers have found that salt clouds are genuinely key to explaining an object's spectrum, and it's a reminder that clouds matter enormously when trying to understand what a distant world actually looks like and why. That's a meaningful statement about the broader field of exoplanet atmospheric science. Not just this one object. Getting cloud chemistry right, rather than simply modeling a clear, cloud-free atmosphere, can be the difference between a model that fits the observed data and one that doesn't. As for the planet's famous pink color specifically, astronomers now attribute that primarily to its combination of extreme age and extreme cold. A planetary mass object this old and this cold ends up with a particular atmospheric chemistry and cloud structure that scatters and absorbs light in a way that produces its distinctive rosy appearance, with the salt clouds forming an important part of that overall atmospheric picture. It's worth noting that our own solar system already has direct experience with unusual, chemically exotic clouds shaping a planet's appearance. Jupiter's own atmosphere features ammonia ice clouds that play a significant role in its recognizable banded appearance. Babaraj has pointed out that Jupiter's atmosphere may have secrets of its own that remain currently out of reach with existing techniques, but that the same kind of detailed spectral analysis used to crack GJ54b's mystery could eventually help resolve some of those questions too, as instruments and methods continue to improve. There's a genuinely interesting parallel worth drawing out here between GJ504b and the giant planets in our own cosmic backyard. Every gas giant in our solar system owes its distinctive visual appearance largely to its cloud chemistry rather than to the underlying gas itself. Jupiter's swirling bands, Saturn's pale golden hue, and Neptune's deep blue color are all shaped significantly by the specific compounds condensing into clouds at different altitudes and temperatures within each planet's atmosphere. GJ504b's pink appearance turns out to follow that exact same underlying principle, just with a genuinely novel cloud ingredient nobody had directly confirmed anywhere before. In that sense, this discovery doesn't just solve one planet's specific color mystery, it reinforces a broader, useful rule of thumb astronomers can now apply with more confidence when trying to interpret the colors of other cold, distant worlds still waiting to be studied in similar detail. It's worth stepping back and asking why confirming salt clouds on one faint, distant object matters beyond simply satisfying curiosity about its pink color. Because this result gives atmospheric scientists a genuine, confirmed real-world data point for a type of cloud chemistry that, until now, existed only in theoretical models. Every confirmed cloud type on a real exoplanet, water clouds, ammonia clouds, and now salt clouds, helps refine the broader toolkit scientists use to interpret spectra from other cold, faint worlds that are difficult or impossible to study through any other method. As more objects like GJ504b get analyzed using similar techniques, researchers will increasingly be able to distinguish which kinds of cold, distant worlds are likely to host salt clouds specifically, versus other cloud chemistries based on factors like age, temperature, and overall atmospheric composition. There's also a genuinely important detail buried within the same dataset that this discovery didn't fully resolve. GJ504b's atmosphere turned out to be unusually enriched in what astronomers call metals, elements heavier than hydrogen and helium. That's a significant finding in its own right, but it deepens rather than resolves the original identity question that has surrounded this object since its 2013 discovery. An atmosphere this rich in heavier elements is consistent with two very different possible origin stories. GJ504. B could have formed the way planets typically do, gradually accumulating material within a protoplanetary disk of gas and dust surrounding its young host star, the same basic process that built every planet in our own solar system. Or it could have formed the way stars do, through the direct gravitational collapse of a cloud of gas, simply on too small a scale to ever ignite nuclear fusion and become a true star. Based on the evidence currently available, researchers genuinely cannot yet say with confidence which of these two origin stories is correct. The reason heavy element enrichment complicates this question so much comes down to how each formation pathway is generally expected to behave. Planets that form gradually within a disk of gas and dust tend to accumulate extra heavy elements along the way, as solid rocky material collects alongside lighter gases, which is part of why gas giants like Jupiter and Saturn in our own solar system are themselves somewhat enriched in heavier elements compared to the Sun. Objects that form instead through the direct collapse of a gas cloud, the way stars typically do, generally end up with a composition that more closely mirrors the original cloud of material they collapsed from, without picking up the same kind of extra heavy element boost. GJ504b's unusually strong enrichment could, in principle, support either story, depending on exactly how enriched the original gas cloud it formed from might have been in the first place, which is precisely why this single piece of evidence doesn't cleanly settle the debate the way researchers might have hoped. That's an honest, meaningful gap in an otherwise successful discovery, and it's worth appreciating rather than glossing over. This research solved one long-standing mystery, the strange spectrum and pink color, while directly deepening a separate, equally fundamental question about what kind of object GJ504b actually is at its core. Both outcomes came from the exact same 2-hour observation, which is a genuinely efficient piece of science, even though it didn't answer every question scientists have about this strange little world. This tension between planet and failed star is actually a recurring theme across a whole category of objects astronomers have discovered over the past few decades, not just this one. Brown dwarfs occupy a genuinely awkward, still debated middle ground in astrophysics, too massive to be comfortably called planets by most traditional definitions, yet too small to ever ignite the nuclear fusion that defines a true star. Objects like GJ504b, sitting right at the upper edge of what's typically considered planetary mass, force astronomers to confront just how blurry that boundary really is, especially once heavy element enrichment complicates the usual mass-based rules of thumb even further. Some researchers argue formation history, how an object actually came together, whether inside a disk or through direct gas collapse, should be the deciding factor in classification, rather than mass alone. Others argue current physical properties matter more than a formation story that, in many cases, can't be directly observed or proven. GJ504b sits squarely in the middle of that unresolved debate, making it a genuinely useful test case for the broader question of how astronomers should even define the line between a planet and a star in the first place. So here's where this genuinely stands right now. For more than a decade, GJ504b, the pink planet, resisted every attempt by ground-based telescopes to reveal what its atmosphere was actually made of, defeated repeatedly by its own faintness and its close proximity to a much brighter host star. In June 2026, a team led by Anish Baburaj finally cracked the case using JWST in about 2 hours, revealing a genuinely rich atmospheric chemistry and, for the first time ever, direct confirmation of salt clouds in the atmosphere of a cold, distant world, solving a theoretical puzzle scientists had proposed more than 15 years earlier, without ever having real evidence to back it up until now, But the same data set that finally explained the planet's strange color and atmospheric chemistry left its most fundamental identity question wide open. Is GJ504b really a giant planet, formed gradually within a disk of gas and dust the same way every planet in our own solar system came to exist? Or is it closer to a failed star, born instead through the direct gravitational collapse of a cloud of gas, simply too small to ever ignite as a true star? The unusually high concentration of heavy elements detected in its atmosphere makes that question genuinely harder to answer, not easier. And as of right now, nobody has a confident final answer. The real question isn't whether distant faint worlds like this one still hold genuine mysteries. This discovery proves they clearly do, even after being directly imaged and studied for over a decade. The real question is whether GJ504b eventually gets definitively classified as a planet, a brown dwarf, or something that still doesn't fit neatly into either category, and whether the same techniques that finally revealed its salt clouds will be the ones that eventually settle that deeper question too. That kind of layered outcome, a real breakthrough that simultaneously deepens a separate older mystery, is actually a fairly common pattern in astronomy, even if it doesn't always get emphasized. Progress rarely arrives as a single, clean, fully resolved answer. More often, it looks exactly like this. One genuine question finally gets settled, using better instruments and more careful analysis than were previously available, while the new data raises the resolution on a different, harder question that was always sitting underneath it. GJ504b's salt clouds are a real, confirmed discovery. Its true identity, planet or otherwise, remains an open one, and that combination is a fair, honest description of where the actual science currently stands, rather than a manufactured cliffhanger added for effect. If you want to be here, the moment astronomers finally determine what GJ504b really is, or when the same salt cloud technique gets applied to reveal secrets about other cold, distant worlds, maybe even parts of Jupiter's own atmosphere we still don't fully understand, subscribe to the channel and turn on notifications, because when that research comes out, we'll break it down here, with the real data, not the invented version. One pink planet, 2 hours of observing time, a decade-old mystery solved, and a deeper one left wide open. Whatever GJ504b eventually turns out to be, this moment, mid-2026, with its atmospheric chemistry finally mapped and its true identity still genuinely unresolved, marks the point where more than a decade of frustrated observation finally turned into real, usable data, even if the deepest question about this strange little world is still waiting for its own answer. Thanks for watching.